Hello, boys and girls. This is Mr. Meyer from Way Happy Studios, and we're going to talk about radical expressions. So, first, we better get some vocab out of the way. You guys all know what a radical is, or in particular, you really know what a square root is. So, here's the square root of 25. Now, let's talk about a little vocab here. This guy right here, that symbol, is actually called a radical. Right? And the guy underneath the radical, he's called the radicand. So when people talk about a radicand, they're talking about the number under the radical. And then the most important thing probably is right here is a number, believe it or not. And that number is called the index of the radical. That number is called the index. Now, over the years in math, we've all kind of said, well, if it's not there, there's a 2 there. And that's why, in fact, when you do the square root of 25, if you've done that, you're like, oh, I factor it down to 5 and 5. And if you have a pair, you can pull it out because you had two things. That was because the index was a 2. And if you had two things, you were able to pull it out, make it a real 5, and wow, you'd had nothing left behind, so you just ignored it and said, hey, the square root of 25 is 5. Now, the interesting thing is, you don't always have to use a radical symbol. Radicals are cool, but they take a long time to draw, and they're sometimes kind of annoying. And I would rather write them as an exponent. So how do I write it as an exponent? Well, back to that 25. If you had x squared equals 25, you probably all know that you would square root both sides, put a little plus or minus in or something like that, and you'd get plus or minus 5. Now, what if you didn't know what a square root was? What's the other way? Well, with the property of exponents, you could raise this side to the 1/2 power, right? Because remember, with exponents, if you have two powers, you just multiply them together. And that would get you x to the first, which would cancel out the squaring. However, in math, you can't just do that to one side. You'd always have to do it to the other side. So if I do that, now I would be down here and I would have x equals 25 to the 1/2 power. That's the same thing as squaring. So in essence, square root of 25 could be the same thing as 25 to the 1/2 power. Or the square root of 9 could be 9 to the 1/2 power. Or why does it have to be a pretty one? Let's go square root of 3. The square root of 3 could be 3 to the 1/2 power. Get the idea? So square roots could be written as square roots if you wanted, but if you just want to raise it to the 1/2 power, that is exactly the same thing. So sometimes on a calculator, I can't find the square root button, and I just raise it to the 1/2 power, and everybody says, ooh, why'd you do that? It's because I understand this property that says, hey, a square root is the same thing as an exponent of 1/2. In fact, it's a fraction. And that's always a tricky part to learn. Now, the cool thing, this works for all kinds of radicals. Cube roots, you have the cube root of 8. That's the same thing as 8 to the 1/3. You have the cube root of 20. That's the same thing as 20 to the 1/3. We have fourth roots in the world. Fourth roots of 6 is the same thing as 6 to the 1/4, and so on and so on. Guess what the 92nd root of 112 is? Yep, 112 to the 1/92. So that's how you could rewrite any root as an exponent, or any radical as an exponent. Now it gets a little more exciting than that. So let me show you this next little clip. What if there's a power on your radical? Right? So if there's a power on your radical, kind of talking about this form right here. If you have some power, you can just rewrite that like that. The power goes on top, and the root goes on the bottom. Now that's something I'm going to steal from Miss Durov, because I really like the way she always explained it. When I was walking by her class, she said, and you have a fractional exponent. The n is the root, meaning the index, right? So that means the index number. And this number is really the power, or the exponent. So notice, there's the power, there's the root. So if you see a fractional exponent, you know exactly where to put stuff. The root should always be in the bottom, because on trees, roots grow on the bottom. And the power, she says the people have power on top, so therefore she puts them on the top. So now let's go through and look at my examples. I have a power of 2 and an index of 3. So if I'm going to rewrite that, I'm going to rewrite it as 15 to the 2/3 power. You can go ahead of me if you want. Try the next one. I have the fourth root of 7 squared. So again, I'm just going to say, hey, that's 7 to the power is 2, the root is 4, so the 7 to the 2/4. Well, we could reduce that and make it 7 to the half. Or 31 to the 1/7. And I'm done, because notice the power is 1 here. There's no real power, so we're just going to put a 1 there. And power to the 1/7. Or right here, ooh, look, the index is missing, the one we're all used to. And just kind of coming back and seeing if it scares you. 7 to the 1/2 power. And that's us writing radicals as exponents. So now let's show you. You're like, okay, I think I got that. I'm feeling pretty good. Let's show you how it can get a little gross, right? Like try this guy. Simplify that. Now there's a couple of ways you can do it. And I should probably mention, like if you have, I don't know, let's do the fourth root of 81 since we need it in this problem. How the heck do you take a fourth root? Same way you took a square root. You factor down as far as you possibly can, all the way down to primes. And then the only way you're getting out of that radical is if you have 4 of a kind. So notice, wow, we do have 4 of a kind, and with nothing left over, I usually cross out my numbers so there's nothing left over, then this is just, answer is 3. Now let's do, what's 81 times 2? 162? Let's do the fourth root of 162. So you would probably say it's 81 and 2, and then you'd have 9 and 9, and then you'd have 3 and 3. And now you go back and you look at that index, and that index tells you to get out, you have to have 4 of a kind. So I'm like, ooh, I have 4 of a kind. So a 3 comes out, but oh, the poor 2 is all by himself, so he doesn't come out. So that would be 3 times the fourth root of 2. And that's how you would reduce a radical. All right, now let's go back to our problem over here. Our problem says, what is the fourth root of 81 x to the 12? So to be honest, I would kind of break this up into 2 parts. I would say this is 81 to the, what power is on the 81? Just a 1, so the 1/4 power. And then I would say x to the 12/4 power. And then I would try to reduce that the best I can. And we just happened to figure out what 81 to the fourth root was. So we know that that's a 3. And I know that this is x to the 3rd power. And look at that. The radical is gone, and there's my answer. And I jump up and down, and I'm feeling really good. Could you do it some more? How about 32 to the 3/5? Challenging enough, right? If I had to rewrite, that's the 5th root, because it's in the bottom, it's a root. It's the 5th root of 32 cubed, or if you don't like it that way, the 5th root of 32, and then that thing cubed. And I think I can simplify that, right? I happen to know the 5th root of 32. If you're not sure, you factor it. You're like 16 and 2. You're like 4 and 4. 2 and 2 and 2 and 2. I cross out everybody I factored so I don't get confused. Whoops, not that 2. He wasn't factored. And then I look for 5 of a kind. So look at that. 1, 2, 3, 4, 5 of them with nothing left over. So I know the 5th root of 32 is just 2. And now if I substitute that in, I get 2 to the 3rd, which I happen to know is 8. So this was just a fancy way of saying 8. All right, let's see if there's anything else I can do. I have 13 to the 4/8 here. 13 to the 4/8, which is just 13 to the half, which is the square root of 13. And that's as far as I can go because he doesn't factor. Or look at this guy. This is 2 to the 27/9, which is 2 to the 3rd, which is 8. So that was just a fancy way of saying 8. All right, let's let you have one, and then I'll see you after the commercial break. All right, nice work. Now I'm sneaking into the next section of the book. So if you're looking at a book, you're saying, wait a minute, why are we talking about graphs now? Well, graphs are the next section, but I figure I could sneak them in and talk to them so we could have more time in class to work on them. And so here's what I got. What does the graph of a radical look like? So look what I did. I went to Desmos and I graphed the square root of x, or x to the half, as you now know. And it looks like this little graph right here that starts at the origin and shoots out. In fact, I like to call these graphs my shooting star because that's what they look like. They look like a shooting star to me. They just kind of boom, take off and go out and head that way. And then I graphed the fourth root of x. And look at that. It's a shooting star, except for you might notice it's kind of a little flatter and then it shoots off, right? And then I graphed the sixth root, and you can see it's even flatter still, and then it shoots off very quickly. And then I put them all on the same graph right here, just so you could see them in all comparison. And you could see the red one, which is the very first one. You could see that it kind of shoots off quicker than the other ones. All the other ones kind of flatten out, and then they shoot off even steeper. And that's true for every even index. So if you have any even radicals, that's exactly what they look like. And you could just sketch them. Notice they all go through the 0.11, which is interesting. But that's exactly what they would look like. Just a shooting star. Now, what if the index is odd? So here's what happens with the index of odd. So again, I went through and did the same thing. I did the cube root, and you can see it kind of looks like this fancy S, right? And then I did the fifth root, where you can see it's kind of flat, and then it shoots off again. Or the seventh root, and I put them all together so you could really see what they look like. But notice the difference between an even index, which doesn't allow negatives under radicals. That's why there's nothing over here, because these are all negative x's, and we're not allowed to have that. And then you have odds, which do allow negatives under radicals. They just have a negative value. So kind of interesting to think of. And that's your graph for all your odd indexes. So now, I don't know how much you've been pounded in your head with understanding translations, but they're the same as they've always been, right? If you have a radical and somebody just, let's go one at a time here in the back, the green one. If somebody adds something to the back, that just moves that radical up or down. So kind of that point that would be sitting right here at the origin, I would just move that point up or down and then make this S shape. Or if it was a shooting star, I would just do the one shooting star shape. That'll move it up or down. You do exactly what it says. If it's +3, you go up 3. If it's -2, you go down 2. Just you do exactly how it is. Now, the ones that are inside the radical make it a little tougher. Whenever they're inside with the x, you always do the opposite. So you can see that this would be an h translation, even though it says -h here. So what that means is this. If you have the square root of x minus 2, that looks like -2, but it actually goes right 2 units. If you have the square or the cube root of x plus 7, that's actually left 7. So you got to be real careful about how to read those. Anything happening to the x is always the opposite. Now, the multipliers, or these guys are the stretches and shrinkers. If the stretcher is inside with the x, kind of, inside the radical, then you have to think of it kind of as the opposite. See how this is 1 over b, and then we talk about b being a horizontal stretch if it's bigger than 1. And if b is smaller than 1, then we call it a compression in the horizontal direction. So again, kind of opposite, because it's a 1 over b, but we talk about if b is bigger than 1, it's a stretch. And then if you look at the number out front, that's not with the x, that's kind of out front of the radical, so that's normal, and you're just going to read that number, and if it's bigger than 1, it's a stretch, and if it's smaller than 1, it's a vertical compression. So think of smushing the graph vertically. Now you guys have to let me know how tricky this stretch and compression is, because it is a tricky topic, and I don't know how much they pounded it in first trimester, but it shows up a lot. And so I always tell people to make sure you always remember, just like exercising, always stretch before you slide. Now these two are your slides right here. These are your slides. And inside here are your stretches. These are your stretches. So make sure you stretch before you slide. So when you read an equation, you want to do your stretching first. And stretching includes reflections over the x-axis or reflections over the y-axis. So stretching includes reflections, and it also vertical stretch or compress. And then you do your sliding. And again, we're going to go over a lot of those in class. So here's kind of our one example, or 2 or 3 or 4 examples that we can sketch and then see what we think. So notice I'm going to graph this first one. Now it doesn't have any multipliers, so there's no stretching, so we're done. There's no flipping because there's no negatives. So all we have to do is talk about the slides. So remember, underneath direction, so that is a right 3, and this guy back here is an up 1. So when I draw my graph, or in this case sketch it, I'm going to go right 3, up 1, and then I decide what kind of graph it is. This happens to be an even, so it's a shooting star. So boom, shooting star. Done. That's all I'm looking for, right? Now look at this next guy. This guy has nothing going on the inside, but he's got a -2 on the outside, so he is down 2 units. Remember, the outside ones, you just read how they are. Don't have to think about flipping them. So I go down 2 and I put a dot, and then I decide what kind of graph it is. Oh, look, it's a cubic, so it's kind of like that S one. It's like a shooting star, and then a not shooting star, or reflected shooting star down and left. And there's your cubic graph. All right, try that next one. Notice that it does have a stretch, right? This is called a flip over the x-axis. So a little heads up, instead of it doing a shooting star this way, it's going to do the shooting star this way. So that's what it'll look like when you flip it over the x-axis. And then you do your slide, which is a left 4 slide. Because remember, it's under the radical, so that means do the opposite because it's with the x. So I'm going to go left 4, 1, 2, 3, 4, big old dot, and then do my reflected shooting star. Woo, there it is, a little sketch. And last but not least, looks like I put in some other gross stuff. Looks like I have a stretch. Now it's on the outside, so that's a vertical stretch of 2, and that's really hard to sketch. And this is on the outside too, so that's an up 3. So when I go to graph this bad boy, stretching first. So here, you can't really show stretching when you sketch, but here would be a cubic graph. Now if I wanted to stretch it, I would go like this, kind of like a little more exaggerated, that I stretched it in the vertical direction. So that's my vertical stretch. But oh no, we got to move that thing up 3. So get rid of all this stuff we put in. Go up 3 and then do your stretch graph. Now how do you do that? You just try to make it a little more exaggerated. But I'm going to be looking for that you wrote the word stretched by a factor of 2, and I'd be like, oh, okay, good job. So there you have your vertical stretch of 2, your up 3, and that's all there is to graphing. You just got to make sure you pick the right graph. Is it an odd or an even index? And you have to be able to read the shifts. Left, right, up, down, flipped over the x-axis, flipped over the y-axis if they do it just to the x, and if it's stretched or condensed. That's it. Have a great day, and we'll start practicing these in class. And make sure you come with your questions, and stay happy.